Okay, so as promised, let's work through the homework problems together here. My intention had been to do this in class, but hopefully this will serve you just as well. Let's start out with problem number 5, where you were asked to figure out or compute the z-score in various situations for a population that had a standard deviation of 10. Okay, so the first one was above the mean by a score of 10. So if we are above the mean by 10, which is a unit of standard deviation, then automatically our z-score would be equal to 1, because the z-score, again, indicates how many units of standard deviation a particular score is above or below the mean. So by the same token, above the mean by 5, that would be half a unit of standard deviation, because 5 is 1/2 of the standard deviation, which is 10. Now we have below the mean by what? By 20. So 20 is 2 units of standard deviation, but we're below the mean. So we have our 2 units of standard deviation, but since we're below the mean, we need to add a negative sign. Okay? And then finally, below the mean by how many points? By 6 points. So for this one, we actually have to do a little bit of a calculation, and the calculation is a bit tricky. Remember, our formula for z equals a given value minus the mean divided by the standard deviation. Okay, so we don't know what the mean is here, but this statement below the mean by 6 points essentially is a summary of the numerator. So that would be 6 divided by our standard deviation of 10, and it is below the mean by that value. So that would be z equals negative 0.6, because 6 divided by 10 is 0.6. And again, we're below the mean, so we have to make it a negative. Okay, so that's how you do those quick ones there. And I hope that you'll understand that for many of these kinds of problems, well, at least the problems in the textbook and the kinds of some of the problems I might give you on an exam, you really don't need to do any computation. You just kind of look at it and see, gee, okay, the standard deviation is 10. We're above the mean by 10. So we're above the mean by 1 unit of standard deviation. So the z-score would be 1. Okay. The idea here is simply to understand that a z-score represents a difference in standard deviation terms. It represents a difference, that's that top part, in standard deviation terms. That's that bottom part. Okay, let's move on now to number 7. So number 7 asks you to deploy the formula and actually to compute a bunch of z-scores. It starts out by telling you that the mean of this population is equal to 50, and the standard deviation is equal to 6, and then it gives you a couple of examples. The first one, x equals 50. So in this case, let's do this one. You actually don't need a formula in this one because the score in question is the same as the mean. So if we were to do that using the formula, we'd have z equals 50, our score, minus 50, our mean, divided by 6, our standard deviation. 50 minus 50 is 0. 0 divided by anything is 0. So our z-score would equal 0. The next one, x equals 62. Well, here we'll need that formula. Z equals 62 minus 50 divided by 6. And that's going to translate to 8 divided by 6. which equals, oops, that should be 62 minus 50, which equals 12. Divide that by 6. We have a z-score equal to 2. Okay, the next one is going to be x equals 53. So again, z equals 53 minus 50 divided by 6. So 53 minus 6 is 3. Again, divided by 6. That's going to equal 0.5. 3 over 6 is a half. So 0.5. Z equals 0.5. Okay, how about the next one? This one, x equals 44. So we have z equals 44 minus 50. Immediately we can see that this will be a negative because we have 44 minus 50. And 44 minus 50 is negative 6. Divided by 6 gives us a z-score of negative 1. So z equals negative 1. And just a couple more. X equals 47. I hope you can see the pattern now. Z equals what? Z equals 47 minus 50. Again, we know that's going to be negative. So that's going to be 47 minus 50 is negative 3. Divided by 6 is negative 0.5. So in that case, z equals negative 0.5. And then finally, x equals 38. So z equals what? Z equals 38 minus 50. Again, a negative. And you can see that the difference there is negative 12. 38 minus 50 is negative 12. Divided by 6 equals negative 2. So z equals negative 2. And I should have put a negative sign over there. Okay, so that takes care of question 7. What's next? Looks like it's going to be question 11. No, we're not actually doing question 11 yet. We have to do part B of question 7. So let's just call this A to keep track of it. And let me go to part B now. In B, we're being asked to do the opposite. We're given a z-score, and again, these same parameters for our mean and standard deviation. But now we're being given a z-score, and we're asked to work backwards and compute a raw score from that z-score. So recall, I won't rewrite the z-score formula for you, but hopefully you remember that it simply represents an algebraic transformation of the z-score formula, the formula we use to get a raw score. So that's the formula. Then it's just a question of plug and chug. So for the first one, z equals 1. So we are 1 standard deviation above the mean. And of course, our mean is 50. Our standard deviation is 6. So we're 1 standard deviation above the mean. So our x value here is going to equal 1 because we're 1 standard deviation unit above the mean. I'll just do this one for you real quick because it's just to get started. It's not really necessary, I think, for this problem to actually do it, but we will anyway. By the way, I've written this as x equals sz, and of course our standard deviation in this case in this problem is for a population. So really, strictly speaking, I ought to write this as sigma, okay? Because for population we use sigma. And that looks sufficiently strange that I'll put a little multiplication sign in there. Okay, so what do we have? We have our standard deviation equal to 6. We have our z-score equal to 1, because that was what was given in the problem. Let me fix this for you a little bit. Make it a little bit clearer what we're doing. Let's slide that on over. Hello, let's slide, please. So again, x equals 6, our standard deviation, times 1 plus our mean, and that is going to equal then, x will equal 56. 6 times 1 is 6, plus 50 is 56. And the next one, they give us z equals 2.5. So we'll do the same thing. X equals our standard deviation of 6 times 2.5 plus 50. In that instance, therefore, x is going to equal 65. Maybe I should have actually done that arithmetic explicitly for you. 6 times 2.5 is 15, plus 50 equals 65. So x, in this case, equals 65. All right, the next one, let's try where z, oops, what's going on here? Z equals 1.5, right? So I'll write it out again. X equals, this time 6 times 1.5 plus 50. So 1.5 times 6 equals 9. Plus 50 gives us an x value equal to 59. And the next one, that would be z equals negative 0.50. So now we're going to be below the mean. So again, we're going to do 6, our standard deviation, times negative 1.5 plus 50. And in this case, this will give us negative 15 plus 50, which is going to give us an x equals, let me just make this the same as the others. So then x is going to equal 35. Nope, that's not right. I see what I did. I used 2.5 in my notes here. So 6 times negative 1.5 is negative 9, actually. So that's going to give us an x value of 41. All right, the next one, this one, z was equal to negative 3. So x equals 6 times negative 3 plus 50. 6 times negative 3 is negative 18. Plus 50 is going to give us an x value of, I think that's going to be 32. Oh, that agrees with my notes. Wonderful. And then our last one, z equals negative 2.5. Here's the one that I missed before. X equals 6 times negative 2.5 plus 50. So x equals, oh, we don't need that there. That equals negative 15 this time, plus 50. And that's going to give us x equals to 35, because 50 minus negative 15 plus 50 is the same as 50 minus 15, which gives us 35. Okay, now we can go on to 11. And let's see what that one is all about. Hello, computer. So this is a classic kind of a problem, and also maybe a classic use for z-scores. Finding out relative position given various means and standard deviations of different data sets. You'll get into this in the lab, because the lab has you comparing scores on a verbal and mathematics assessment using SPSS. So let's work through these by hand. This is, again, number 11. Okay, so you receive a midterm exam for 4 classes, and in each of the classes, your score is a 70. But each of the classes has a different mean and standard deviation. So for the first class, the mean was 70, and the standard deviation was equal to 10. Your score was 70, so your score was the same as the class score. So the z-score for that one would have been 0. So you did exactly the same as the mean. Because again, going back to our z formula, which is written as z equals our raw score minus the mean divided by the standard deviation. In this case, this x minus x bar is 0. So again, any number, 0 divided by any number is equal to 0. So that one was easy. Let's take a look at the next one. We'll call this A. I don't know if the book numbers these or not, but we will just for our purposes here. The mean in this class was a 50. The standard deviation was 20. Your score was 70, so immediately we know that you did above the mean. So let's take your score, which was 70. Again, 70 up here. And let's subtract that from the mean. It's 50 divided by 20. And you can see 20 divided by 20 equals 1. So you scored 1 standard deviation above average, 1 SD above average. So you can be pretty happy about that, how you did in that class, whatever class B was. How about class C? Let's see. We have a mean in this instance of 80. Standard deviation, I'll write it as sigma. Standard deviation is equal to 20. No, standard deviation is equal to 5. You scored a 70, so you did less than the mean. Your z-score would be 70. Your score, again, minus 80 divided by 5. Divided by 5. And that's going to be negative 10 divided by 5, which gives you a z-score, z-score of negative 2. So you did a lot worse in this class. Time to study a bit. Z equals, let me make sure that looks like a Z. It doesn't, it's not supposed to look like a Z, it's supposed to look like a 2. Okay. 2 SD below. Well, just negative 2 is fine. Z equals negative 2. How about class D? Did we do better in class D? Here the mean was again 80. Oh boy, I'm not looking forward to this one. And the standard deviation though, well wait a minute. The standard deviation was equal to 20. So again, you did Z would be equal to your score of 70. Again, minus the mean, but in this case, there's a lot more spread in the class. Standard deviation for the class was 20. So before I figure it, try to think, what do you think it's going to be? What do you think it's going to be? You think it's going to be better or worse than in class C? Well, it's still going to be below the mean. You can't avoid that. But a lot of people scored below the mean. Negative 10 divided by 20, and that's going to give us a z-score of negative 0.5. So yeah, you did worse than the class did, the class average, but there was a lot of spread, so you were not as much of an outlier in this particular instance. Okay, just a couple more to do here, I think. Let's take a look at 25. So this is the same kind of problem. Problem 25, A and B are the same sort of problem as the problem above. It's just worded a little bit differently. For each of the following, identify the exam score that should lead to a better grade. In each case, explain your answer. All right, so in the first case, we had your score was a 70, and the mean for the class was an 82, so you already did worse in the class, with a standard deviation of 8. So let's figure out a z-score first for that one. So z is going to equal what? It's going to equal your raw score minus the class mean divided by the standard deviation. Okay? So that's going to give us here, this is negative 12 divided by standard deviation, gives you a z-score of negative 1.5. Okay. In your other class, we'll write that one over here, you scored a 60, and in this instance, the mean for the class was what? It was 72 with a standard deviation of 12. You need to do some studying because you are consistently below the mean here. That's not a good thing. So let's again compute the z-score. Z equals your score of 60 minus 72. Minus 72 divided by that z-score, that standard deviation of 12. So that's going to give us on top here negative 12 divided by 12. And your z-score is going to be negative 1. So yeah, looks like you did better in this class. Even though you were below the mean by the same amount in both instances, the fact that the class average had a higher, that the class on average had more dispersion, there was more variability, you're not quite an outlier the way you are here. And I use the term outlier here just in a generic sense, not as we've been discussing box plots and interquartile ranges and that stuff. You're further from the mean in the first class than you were in the second class, even though the actual distance from the mean in both instances was the same. All right, let's take a look at part B. And I think in part B, we have you do the same thing, but the numbers are a bit different. In the first class, you scored an 85 on an exam with a mean of 49. Wow. Oh, not 85, 58. You scored 58 on an exam with an average score of 49 and a standard deviation equal to 6. So you can see right away, at least in this scenario, you're doing a bit better. So first we compute a z-score for this. So that's 58 minus 49 divided by 6. 58 minus 49 is equal to 9 divided by 6 gives us a z-score of 1.5. Okay? And how about class 2? Or the second scenario. In this case, you got an 85 on an exam with an average of 70. Average of 70 and a standard deviation of 10. So again, our z formula equals that score of 85, your score, minus 70 divided by 10. So in this case, we're going to have 15 over 10, and that'll give us a z-score of 1.5. Okay, so looks like you scored the same on both. Did I do that right? Yes, I did. Okay, yeah, the same on both. Your grade was different, but the mean was different in each class, and the standard deviation was different in each class. So this two scores should lead to the same relative position That is relative to your classmates and relative to the mean. All right, let's go on to 27. Okay, so here we are with problem 27. And in this case, a population with a mean of 41 and a standard deviation of 4 is transformed into a standardized distribution now with a new mean, and let's call this mu prime, and let's call this sigma prime. So it's transformed into a standard deviation to a new score, or a new mean rather, of 100 and a standard deviation of 20. Find the new standardized score. Find the new standardized score for each of the following values from the original population. So the first one is 39. So, all right, what's this asking to do here? Let's remember that a z-score contains all the information that you need about a score's position relative to the mean and relative, therefore, to every other score in the distribution. Our original population had a mean of 41 and a standard deviation of 4. So what we need to do is first to compute this z-score, again, because a z-score contains all the information that we need about a score's relative position to a mean. Here, we have the relative position, here, the new mean will be 100, so we need the relative position of a score of 39 on this distribution. And now we need the relative position of that score on a new distribution, a new set of scores, not a new set of scores, a transformed set of scores with a mean now of 100 and a standard deviation of 20. So first step is to compute our z-score. Again, because the z contains all the information we need about these relative positions. So I'll just rewrite the z formula just for fun here. Let me use mu divided by sigma. Okay, so for this case, we have a score of 39 minus a mean of 41, a mean of 41, divided by a standard deviation of 4. So this is going to give us a z-score of minus 2 over 4. Okay, and that is equal to negative 0.5. So now we have to do that transformation. And to do that, we go back to our formula that we used in the previous question. This time we'll call it x prime, and that is going to equal our z-score times our new standard deviation, which we'll call sigma prime, plus our new mean, which we'll call mu prime. So let's figure that out. In this case, our z-score is 0.5. We're going to multiply that by our new value for the standard deviation, which is 20. And we're going to add our new mean, which is 100. So that is going to give us 0.5 times 20 is 10 plus 100. So x prime equals 110. And I don't know how many of you captured or that I made a careless mistake or noticed that. Our z-score is negative 0.5, not positive 0.5. So it should be negative 0.5 times 20, which is negative 10. Negative 10 times plus 100 is actually x prime equals 90. Okay? How many of you caught that? Be honest. For B, we have a raw score of 36. So we'll do the same, we'll use the same formula. X prime equals our z-score of, oh no, we have to figure out the z-score. That's too bad. So our z-score equals 36 minus 41 divided by 4. That's going to give us a z-score of 36 minus 41 is 5. Negative 5 divided by 4 equals negative 1.5. And now we calculate our new raw score. X prime equals negative 1.25 times our new value for standard deviation, which is 20, plus a new value for our mean, which was 100. This becomes negative 25 plus 100 gives us a raw score here of 75. So x prime for that score of 36 in the first distribution is going to be equal to 75 in the new distribution. And the next one is C, and in this case the raw score was 45. So again, we need to compute that z-score because the z-score, again, contains all the information you need about the relative position of a score to the mean, which enables us to rescale that raw score. So z in this case is going to equal 45 minus 41, our mean, our original mean, divided by our original standard deviation of 4. And that gives us a z-score equal to 1. So let's rescale this now. X prime equals our z-score of 1 times our new standard deviation was 20, I think. I hope it was 20. Yes, it was 20. Plus our new mean. And this is going to give us a score of 20 plus 100, which equals 120. And finally, D, our raw score was 50. Again, we need to compute that z-score because, again, it gives us the relative position of everything. So we have 50 minus 41 divided by 4. And that is going to give us 9 over 4, and 9 over 4 is equal to 2.25. And to figure x prime, we're going to take that z-score of 2.25, multiply it by the new standard deviation, the desired standard deviation, I should say, and add our desired mean, and that will give us 145. Okay. Here's the intermediate step, by the way, sorry. 2.25 times 20 is 45, plus 100 is where we get that 145. Okay? All right, just one more problem. I think it's 29, that was 27. Oops. $29. Well, 29 is kind of cumbersome. It'll take a while to work through, but it's just a question of sticking with it. In this case, we're given just a bunch of raw scores, and we're asked to compute the mean and standard deviation of these scores, then to compute the z-scores for each, and then to transform those z-scores so that we have a new mean of 50 and a new standard deviation of 20. So here are the scores. Let's say 6, 1, 0, 7, 4, 13, and 4. So the first thing we need to do is compute our mean. If you add these up, you'll find that they add to 35. And how many scores do we have? 1, 2, 3, 4, 5, 6, 7. That doesn't surprise me because the book likes us to be able to do our math without a calculator. So the formula for the mean, I'll use mean. I'll use mu rather, is going to be the sum of the values divided by n, and that's going to equal 5. Well, let's show you explicitly. The sum of the values is 35. Divide by 7 gives us a mean of 5. Oh, wait. Okay, so now we need to compute the standard deviation. How do we do that? Well, hopefully you remember. I'll draw out a table for us. Let me move this a little bit out of the way for right now. And let's work on our table. So we'll call this, we'll call that x. We'll call this x minus mu squared. We'll do the whole operation in one fell swoop, but I will write them out for you. So that's 6 minus 5 squared equals 1. And then 1 minus 5 squared. 1 minus 5 is 4. Square that is negative 4. Square that, we get 4. We get 16. And the next one we have is 0 minus 5 squared. And 0 minus 5 is negative 5. Square that, we have 25. And 7 minus 5 squared is positive 2. Square that, and we're going to get 4. And then 4 minus negative 5 is negative 1. Square that, and we'll get 1. And 13 minus 5 is 8. Square that, and we're going to get 64. And finally, 4 minus 5, square that, that's negative 1. Square that, we get positive 1. Okay, let me write out here the formula for standard deviation. Standard deviation equals, well, it equals a couple of things. First of all, you might say it equals simply the square root of the variance. That's not that helpful because we still need to know how to calculate that variance. And the variance, I'll write the whole thing out all in one big thing here, is going to be, it's going to be the sum of squares. How will I write that? SS divided by n, and we'll take the square root of that. Okay, so we need the sum of squares. So that is this column over here. That's this column over here. And we get a sum of that column, and that's going to be 112. And yeah, I'm good at sum arithmetic, but of course I've already worked out the problem. So, all right. So our sum of squares is equal to, well, we'll do it like this. Our sum of squares is equal to 112. I have to divide that by our 7. And that's going to give us, this equals 16, by the way. That equals 16. Square root of 16 equals 4. Okay, so now we have our mean over here. We have our standard deviation over here. And now we can start computing those z-scores. To compute the z-scores, we'll need the raw scores again. So let me copy them back down. Oops, let me copy them back down here. X equal, so let's do it like that. Let's do x 6, 1, 0, 7, 13, 4, and 5. If you feel sorry for yourself because you've got to do all these calculations, just imagine the poor guy who had to come up with the question. By the way, it wasn't me. He had to work it out so that all of these numbers would be easier for you to work with without a calculator. So bear that in mind as you struggle through doing these. So for the z-scores, we need x minus mu divided by our standard deviation. So copy that back down here. Mu equals to 5, I think it was. Standard deviation was equal to 4. Is that right? Yes, it is. Okay, so let's do it. So the first one, we're going to have 6 minus 5 is 1. 1 divided by 4 is 0.25. Now, let's do it explicitly. We'll put z over there. So let's do 6 minus 5 divided by 4, and that equals 0.25. Okay? And the next one is 1 minus 4 divided by 4. 1 minus 4 is negative 3 divided by 5 is, divided by 4 is negative 0.75. Oops, I made a mistake. I subtracted by 4 instead of 5. So if we make that a 5, we have negative 5 over, we have negative 4 over 5, and that will give us a z value of 1. Okay, negative 1 rather. Okay, let's take a look at the next one. 0 minus 5 over 4. 0 minus 5 is negative 5 divided by 4 is going to be negative 1.25. Okay, 7 minus 5 is 2 divided by 2 is positive 0.5. And the next one is 13. 13 minus 5 is 8. Divide that by 4, and we get a value of 2. And then 4, next person scores 4, minus 5 is negative 1. Divide by 4 is negative 0.25. And the next person scored a 5. So 5 minus 5 is 0. Divided by 4 is still going to be oh, I see why these don't agree, because this score should be a 4. And in fact, if you look at the textbook, that 4 went over there, the 13 went over there. It should really, in the textbook, it's 4, 13, and 4. I don't know why I did it that way, but the numbers are correct anyway. So that's, again, 4 minus, and we get the same thing we did before. Okay, so now we have all our z-scores. Now we have to figure out x prime. We need to figure out what happens if we change our standard deviation and our mean to something new. The something new in this case is going to be mu prime equals 50 and sigma prime equals 20. So let's plug that in. X prime equals our standard deviation, our new standard deviation. Let me make it a sigma. Sigma prime times z plus mu prime. Okay, so let's work that one out. Let me just slide this over a bit. Oops. No, doesn't matter. Let me slide this over a bit. And I think just in the interest of space, I'm going to use a different color now. I'll call this mu prime, and let me not use something that's quite that thick. A little bit easier to read. Call that x prime. So for our first one, we're going to take our new mean, which is 20, multiply it by z, plus our new mean of 50. And 20 times 0.25 is, 20 times 0.25 is 5. So our first one will be 5 plus 50. And our raw score x prime is 55. For our next one, again, we'll have that 20. This time times -1 plus 50. And that will give us a value of 20 times -1 is -20 plus 50 gives us a value of 30 for x prime. And the next one, again, 20 times -1.25 plus 50. 20 times -1.25 is -25 plus 50 equals 25. Oops, where are you? 25. And the next one we have is, again, 20 times 0.5 is going to give us a score of 60, because 20 times 0.5 is 10, plus 50 is 60. Our next one is we have, again, that new standard deviation of 20 times 2 this time, plus 50. That'll give us a x prime value of 90. And then our last two are the same. It is negative, well, let's do it the same way we've been doing it. 20 times -1.25 plus 50. That is 5. -5 plus 50 is 45. And of course the same thing for the next one. Oops, I see that I answered it correctly, but I wrote in the wrong value. It should be -0.25 for that z-score. Okay, so 20 times -0.25, and that equals 5 plus, -5 rather, plus 50 equals a raw score, a rescaled score of 45. Okay, well, I think that's it. And I hope that you found that useful.